So we've been looking at complex numbers in the rectangular coordinate, converting them into polar coordinates, and then, or polar form, and then also converting them into exponential form. And so, for instance, if we had z is equal to x plus iy, we could rewrite this in the form where we had z is equal to r all times cosine theta plus I sine theta, or equivalently, z is equal to r e to the I theta. So we should be able to go back and forth between these. R, that was equal to the length of the hypotenuse if we graphed our point. We had our horizontal axis was the real number system, and the imaginary axis was the vertical axis. So I just muted everybody. If anybody has a question, just unmute yourself and then ask. So R was equal to the square root x squared plus y squared. Theta, this was equal to tan inverse of y over x. And what else we have? X was equal to r cosine theta. And y was equal to r sine theta. So de Moivre's theorem, we were looking at operations of complex numbers multiplying and dividing. If we were multiplying two complex numbers, we multiplied our R values together and we summed our angles. And if we were dividing, then we divided our R values of the complex numbers and we subtracted the angles. And for de Moivre's theorem, this is saying if you raise, if z is equal to x plus iy, and we want to take z is raised to the nth power, then in the other forms, you can say z to the n is equal to r raised to the nth power, all times cosine n times that theta, plus I sine n times theta. So usually here, if our value theta is not between 0 and 2 pi, we can rewrite it. So find coterminal angles. If this is not between 0 and 2 pi. Including. And then we could also rewrite this in exponential form. So exponential form would be same idea with our angle. Z to the nth is equal to R to the n. And this was E I n times theta. So let's look at one of those. We ended with an example yesterday. We didn't finish where we got that value in between 0 and 2 pi, but we were almost there. Let's just start with a new example. So let's say you had 1/2 all times cosine to 2 pi fifths, and then plus I sine of 2 pi fifths. And this quantity is raised to the 5th power. So write each expression in rectangular form, x plus I, yi, and in exponential form, r times e to the I theta. Okay, so when you are doing these, the first thing that you want to do is you want to graph this. And so if we were in rectangular form, then you would graph the point. If it's in here in polar form, we can also graph the point. And so let's, for a minute, ignore this fifth power. And I'm missing a bracket or parentheses. So technically, that 1/2 power is in there. There we go. Okay, so we first want to graph this. We need to figure out our angle. Our angle is 2 pi fifths. So we want to graph 2 pi fifths. And by looking at this, you should see that r is equal to 1/2. So graph 2 pi fifths. If you're not exactly sure where that is, we can convert this into degrees. And we know that 2 pi fifths times 180 over pi is going to give us the degrees. So pi's cancel. 5 goes into 180. 5 goes into 18 3 times, so 36 times. So this is 2 times 76. So this gives me 72 degrees. Okay. I'll leave it in 2 pi fifths, but I just kind of needed to know where I was going to place this and which quadrant I was going to fall in. So we got an angle of 72 degrees, or 2 pi fifths. And this r value is how far we're going up, which is 1/2. I'm just going to make my 1/2 up here. So we want to figure out what x and y are. We know what this length is, and we know we have an angle in here. So think about what you know. We have an angle, and we know the hypotenuse. And we want to find the opposite side, and we want to find the adjacent side. So looking at this, so y is x. Well, cosine of 2 pi fifths is equal to, well, adjacent x all over r, which is 1/2. If we multiply both sides by 1/2, x is equal to 1/2 cosine of 2 pi fifths. Y, we know that sine of 2 pi fifths, right? This is equal to the opposite, which is y, over the hypotenuse, which is 1/2. We multiply both sides by 1/2, we have y is equal to 1/2 sine of 2 pi fifths. So without remembering that formula, x equals r cosine theta, because I guess we could have looked at this and said, well, we know what r is. We know what theta is. Well, we know x has to be r sine theta. Cosine theta, and y has to be r sine theta. So 2 pi fifths is not one we know. Make sure that you're in radians if you're, make sure again, nope, I'm in degrees now. So radians. And we're going to look at cosine of 2 pi fifths. And that gives you approximately 0.31. So let's do the same thing. No, actually, that's not times my 1/2 though. That's just the cosine of 2 pi fifths. So times 0.5. So this is about 0.155. Really don't want to round, but that's okay. Sometimes you got to. So sine of 2 pi fifths. Take that result, which is about 0.95, and multiply it by 1/2. And we get about 0.475 or 6.
What did the x equal? 0.155?
Yeah, 0.155. You know, I don't know really why I'm going through all this work. Technically,
I'm sorry. I was about to ask, like, so what was the example? Like, what are we trying to move to? Is it rectangular form?
Yeah,
or?
rectangular form, but technically it would have been easier. So let's just say this example didn't have that 5th power. So this is kind of review without that 5th power. And then let's go back and then we'll rewrite that with or we can do that example with a 5th power, but I don't know why I was going through all of this. I'm going back to what we were doing at the beginning of this section. And so if I was converting this to rectangular form, which we do have to, but what I'm doing now is much harder. So rectangular form right now, this is 0.155. Oops, and it's not a point. 0.155 plus, and our I value is 0.476 I. And this would be what Z is. If I wanted to rewrite this in, so let's just review, exponential form. Then this was E. Z is equal to R, which is 1/2, E to the I theta. And theta in this case is 2 pi fifths. Okay, I apologize about that. Z is equal to, let's go back to, we want to do that same one. So Z is equal to 1/2 all times cosine of 2 pi fifths plus I sine of 2 pi fifths. And they ask us now to take that and raise that to the 5th power. And so if we want to do this, we don't have to go through all that mess that I was just doing. We can use the theorem. So this says that Z raised to a power n, we're going to use this theorem, is R to the n, all times cosine of n times 2 pi fifths plus I sine of n, which in our case will be 5 times 2 pi fifths. So using this formula, we have Z is equal to 1/2, all raised to the 5th power. And then this is cosine. Well, n is 5, so 5 times 2 pi fifths plus I sine Well, n again is 5, so 5 times 2 pi fifths. Okay, there we go. So 1/2, and I'm raising 1 to the 5th power. So 1 times 1 times 1, 5 times is 1. 2 to the 5th power is 32, is equal to, or times cosine of 2 pi plus I sine of 2 pi. So rectangular form, this would fall out. This is in, right now, this is in our polar form. Rectangular form, just evaluate it. So cosine of 2 pi, well, that's a full revolution. That gets us to a positive x-axis. X is 1 on the positive x-axis, so this would be 1 over 32, all times 1 plus I, but sine of 2 pi, on the x-axis, sine is 0. Your y value is 0, so that's times 0. So this is equal to 1 over 32. So our imaginary part, there's no imaginary part in here. And then we had, the exponential form.
What was the formula you were following for the rectangular form?
All I was doing was coming up here to the polar form and evaluating it. So we had just found the polar form, so I have the 1 over 32 here, and then I know cosine of 2 pi is 1, and I know sine of 2 pi is 0, so 0 times I is 0. And then I have this just 1 over 32 times 1. So if you have your angles and what your R is, and it's in polar form, you can, if these are angles that we know, we can figure out, or if we have the calculator, we can get an estimate. And so this is in the form of z is equal to x plus iy. And so in here, our x value of our would be 1 over 3 over 2. And our imaginary part would be 0. But in exponential form, it is equal to r e to the I theta. Our r value, just looking at the, after we took the 5th power, our r value was 1 over 32. E, I, and our theta value is 2 pi. And so there's our exponential form. Oops. Okay, so this is where, oops, 2 pi theta. Why do they? That's an error. Oh. They converted 2 pi to be 0. So remember theta, we were choosing theta to be between 0. It included 0, but not 2 pi because we don't want the same value, and those would give us the same value. So this is the same thing. As 1 over 32 e to the I times 0. Which, notice if we reduce it, would give us our rectangular form 1 over 32. Because this would really be e to the 0 power, which is 1. 1 times 1 over 32 is 1 over 32. Okay, so that brings us to another theorem. So this was where we were taking the nth power. Well, we're now going to look at taking roots of complex numbers, but remember square roots are the same thing. They could be rewritten as powers. So that theorem is going to kind of, pretty much be almost identical. So theorem, which is finding complex roots. And again, they like to use Euler form in your book. I'm just not used to that, but I will write it out in that too, because we will just convert into all three forms, so you're comfortable with it. So suppose that you have W is equal to R times e to the I theta is a complex number. We're given that n is a number that's bigger than or equal to 2 and is an integer. Our value of W just can't be 0. Then there exists, or there are, n distinct complex roots of W, given by the following formula. I'm just going to write it like this. So if we're trying to take the nth root of W, well, we're going to take the nth root of our R value. So like this is the same thing as W, right? Raised to the 1 over n power if we rewrote this in exponential form without the radical. And so our R value is going to be raised to the 1 over n. Just follows kind of de Moivre's theorem. And then we have E, I, and this is all times. Now this is where we have to be a little bit careful. It's I 1 over n all times theta plus 2 pi k. I'm going to put the n in the denominator there instead of multiplying by 1/9, but that's the same thing. So this is the same thing. E to the I. So normally it would have just been theta over n, or n times theta. This time, if it's a root, we have to think of 2 pi k in there. So k is a value. We have to start k as the integer 0. We're going to look at k when it's 1, and we're going to go up to the value 1 less than what n is. So if we're looking at the cubed root, we would look at when k is 0, 1, and 2. If we were looking at the fifth root, we would look when k is 0, 1, 2, 3, 4. If this was squared, we'd only have to look at 0 and 1. So we're looking at k being between 0 and -1, those integers. So let me just rewrite this in polar form. So this would be R all raised to the 1 over n power, or we can think of it as the nth root if we want of R. and this is cosine of theta plus 2 pi k all over n plus I sine of theta plus 2 pi k over n. Okay, so let's look at an example. Okay, so find all the complex root, write your answer in exponential form. So find the complex cubed root of -8 minus 8i. Okay, so basically we're saying if we have z is equal to -8 minus 8i, we want to figure out what is the cubed root of z. And by our theorem, there has to be 3 distinct complex zeros. So we need to actually convert this. So I'm going to convert it to polar form. So I have -8, -8. So if I go over left 8 and down 8, we have our triangle now. We can figure out what theta is, and we can figure out what r is. So r is equal to the square root of 8 squared plus 8 squared. So r is equal to the square root of 64 plus 64. So r is equal to the square root of 128. Well, 4 goes in there at least. And the square root of 4 is 2. So this would be 2. Let's see, 4 goes in there 3 times and twice. So 32 has a factor of 4 because that's 8 times 4. Actually has a factor of 16. So bear with me, square root of 16 is 4. And we would be left with a 2. So r is equal to 8 root 2. And then...
Excuse me, Professor.
Yeah.
I have a question on the cube root of z. So why did you put a cube root there?
Because it said it wanted us to find the complex cubed root. And so the cubed root is like this. And I defined z to be what this complex number, what we were taking the cubed root to be.
Oh, okay. So the direction would tell us like what number to use.
Yeah, exactly.
Okay, thank you.
You're welcome. So we got to figure out what theta is. So let's think of this as our reference angle right now. And think about what trig functions you have. So if we're thinking about trig functions and we want to do opposite and adjacent, well, we know that tangent is equal to 8 over 8. Which is 1. And so you're trying to think about what value of tan gives you 1. And that would be 45 degrees. Or pi force. but we're in quadrant. Our angle is in quadrant what? 3, and tangent is positive. Well, it doesn't matter if tan is positive or negative, it doesn't matter. We just need to go down 45 degrees or pi fourths. So we have a pi here plus a pi fourths. So we have a 4 pi fourths plus a 1 pi fourths. So our theta value is 5 pi fourths. So right now, if I rewrote z in the polar form, that negative 8 minus 8i, z would equal our r value, which we saw was 8 root 2 cosine of 5 pi fourths plus I sine of 5 pi fourths. But I wanted us to take the cubed root. And I'm wondering if really actually right now, if we don't keep this as a radical, if we kept it as a square root of 128, that might help us later. I don't know. Or we're going to have radicals and radicals under radicals, which I guess we've dealt with before. So it's up to you. But now we're going to take the cubed root of that because it wanted us to take the cubed root of this number. So we have the cubed root of our r value, which we can either say is a square root of 128. I guess that's a square root anyway. So let's say just do 8 square root of 2. There we go. And then we have all times cosine 5 pi fourths plus 2 pi k. So this is where it might be easier if we multiply by 1 over n, and n is 3 in our case, instead of dividing by 3, because we have a complex, we'd have a complex fraction. So we're going to multiply this by 1/3. Plus I sine 1/3 times 5 pi fourths plus 2 pi k. Come on. Okay, we have another step though. We have with it the roots, we have to look at k equals 0. We have to look at when k is equal to 1 and when k is equal to 2. I noticed that I can take, if I have a cubed root or a root, and what's underneath that is multiplication, strictly multiplication, we can break that down as the cubed root of each piece and then multiply it. And so cubed root of 8 is actually just 2. So we have 2, and then we'll have the cubed root of the square root of 2. We'll fix that later. So cosine, when k is 0, that makes 2 pi k go to 0, and then we would have 1/3 times 5 pi fourths. If we have 1/3 times 5 pi fourths, that gives us 5 pi 12ths. Plus I sine, same idea, this would be 5 pi 12ths. So this right here can be rewritten also in exponential form. Actually, this is the cubed root of z. Let's clean up the cubed root of the square root of 2. So if you think of that as radicals, or those radicals as exponents, the cubed root is the same thing as a 1/2 exponent. So I'm just going to kind of do the work up here. So I'm just rewriting the cubed root of the square root of 2. Well, the cubed root is the same thing as a 1/3 power. And the square root of 2 is the same thing as 2 raised to the 1/2 power. Power to power, you have to multiply. So this is 2 to the 1/6 power. And so now I can rewrite this as a single radical. And this would be the 6th root of 2. That's just this piece right here. So we have 2 times the 6th root of 2. And then E, I, and then our angle here is 5 pi 12ths. So there's one of them, of the roots of that complex number. We can find another one. So that was when k is equal to 0. We have to look at when k is equal to 1. Okay, I know I need to clean this up over here because I'm going to have to get a common denominator. K equals 1. So I don't know if we want to do the work on the side and then come back to it. We'll have 1/3 all times this 5 pi fourths plus 2 pi times 1, which is 2 pi. So we have 1/3 all times, I'm going to need a common denominator. So this is an 8 pi fourths. 2 pi is the same thing. So 8 pi fourths plus 5 pi fourths is 13 pi fourths. Now if I multiply through by that 3, I get 13 pi 12ths. So if we have k is equal to 1, then we can rewrite it. Let's just do it in green then. So the cubed root of z, if you wanted it in this polar form, that is going to be, let's just rewrite that 2 cubed root of the square root of 2 as what we found to be 2 6th root of 2 cosine of our angle, which is 13 pi 12ths, plus I sine of 13 pi 12ths. And in exponential form, we could rewrite it. This is our R value, which again is 2 6th root of 2 e to the I theta. And theta in this case is 13 pi 12ths. So one more value we have to look at, and that's when k is equal to 2. So let's just kind of, again, do some side work. So when k is equal to 2, we have that 1/3, the root we were taking, of theta, which we found to be 5 pi fourths, plus 2k, so, or 2 pi k. So 2 pi times 2, so that's plus 4 pi. We need a common denominator again, so I'm going to multiply 4 pi by 4 over 4. So that's 16 pi fourths plus 5 pi fourths is 21 pi fourths. All times the 1/3 out front. So this is 21 pi twelfths. So again, if we wanted to put it in polar form, the cubed root of z is equal to 2 root 6 root 2 cosine of our angle, which is 21 pi twelfths, plus I sine of 21 pi twelfths. And last but not least, the cubed root in the exponential form is 2 6th root of 2 e I to our angle, which was 21 pi twelfths.
Professor.
Mm-hmm.
So those two equations would be the answers.
So if it depends on what form they want. So if they just want exponential form, then you would just write it this way. And there's going to be 3 answers because it's a cubed root. If they wanted it in the polar form, that's where you have to write it this way. And this way.
And then rectangular is the one where you actually evaluate the polar form, right?
Yeah, so then we can do the rectangular form, and these aren't going to be pretty, but we could do it. You couldn't do, we don't know, 13 pi twelfths, and so we could put that in the calculator and get those values. You could also graph these. So it basically is saying that we have 3 roots of that complex number. And so we could figure out, you know, what is each one of those angles. And then we're going to go out our R value of 2 times 6 root 2. So I would have to convert these technically to figure out what my degrees are to be able to graph it more. So if I had 5 pi twelfths was one of my angles. So this is 180 over pi. That's 75 degrees. Maybe call this theta sub 1. Theta sub 2. When k was, or I guess we could call that 0 because that was k was 0. This was 1. Let's convert that. That was 13 pi twelfths. Converting it to degrees, so 180 over pi. We get 195 degrees. And then theta sub 2. So this was 21 pi twelfths times 180 over pi. 12 goes into 180 15 times. Oops, that should be a 21. And so 15 times 21. So that's 315 degrees. And then we just figure out what R is. So R was 2 6 root of 2, just to estimate. I was just recognizing that these are the same base. We can pretty much just add our exponents, but that's okay. Let me just do the 6 root 2. So raised to the 1/2, or 6 root 1/6. So that's approximately 2.2. And so 75 degrees go out about 2 root 2. 195 degrees, go out 2 root 2. And then 315 degrees. So what is this? 270. So about right here. And go out 2 root 2. I'm sorry, 2.2. So that is that. So basically then I'd go into my calculator, do my 2 point, we know X is equal to R sine theta. Or sorry, I keep on saying that. X is equal to R cosine theta and Y is equal to R sine theta. And so you could figure out what the X coordinate is of the rectangular coordinate of the complex number and the Y value coordinate, the imaginary part of the complex number. Okay, so that is complex numbers and trigonometry with polar coordinates and Euler's form, which is the exponential form of a complex number. So now we're going to get into vectors, the last piece, the last topic in this course.
On the exam, will it be given like which one, like the exponential like formula thing, rectangular and all that?
I can do that. I can give you those.
Okay, thank you.
So vectors. Well, there's different ways to approach vectors. Vectors, we are going to look at it in the geometrical approach and an algebra approach. Basically, all vectors they're basically lines. Well, not technically lines, but they have a point and then kind of an arrow. And vectors have magnitude and direction. Vectors, how about this, is a quantity that has magnitude. Okay, so magnitude is just the distance or length, and direction, so that's, how far are we going? So for instance, the plane was heading, north 45 degrees east at 500 miles per hour. You were given both direction and you were given a magnitude, in this case, miles per hour. Where if you were looking at an area of an object, that is just one quantity, and that we would call as a scalar quantity. So let's start there. I just took a little bit of notes. Okay, so we're just going to kind of get into some terminology of vectors. And so let's say you had some point P and you had some point Q, or how about P? Yeah, P and Q. And you had an arrow starting at P and going until you hit Q. P, the point here, is called the initial point, and Q is called the terminal point. So the vector joining P and Q can be written the following. Ways. So a lot of times when you see vectors, if they're in text and like a textbook, or typed, it's going to be bold. But that's hard to do when you're taking notes or you're writing out solutions. And so to note vectors, what you do is you write an arrow over the vector, whatever it's called. So we could write the vector PQ as PQ with a line over it. If we let V equal the vector PQ, then we would write V with a line over it, or you might see it with bold text. But I'm not going to do it that way. I'm going to have it with an arrow over it, denoting that it's a vector. You can have a zero vector. So you would denote the zero vector with a 0 and a bar over it. Vectors are equal to each other if they have the same magnitude and direction. So vectors are equal to each other if they have the same magnitude and direction. Okay, so let's say you had some vector out here. This is our vector V. If I had some other vector, I don't know, in a different spot right here, but it was heading in the same direction and it was the exact same length, W, we could say that these two vectors were equal to one another. It doesn't matter where it is, just as long as it's going the same direction, kind of pretend they are if they aren't, and the same length. It's a little off. So these are all the same vectors. If we look at a number times a vector, so let's say that alpha is equal to a real number. Alpha doesn't equal 0. Then alpha times a vector, I'm just going to call it V, is equal to, it's going to have the same direction. Well, actually I should say one thing. Two cases can happen. Alpha can be greater than 0. So let's just say alpha is also greater than 0. We'll talk about if it's negative in a minute. So it has the same direction. The magnitude is just multiplied by alpha. Okay, so again, magnitude is the length. And so let's talk about how to get that length. And so if we have our vector again, V, well, if we put it on our coordinate system, we could, doesn't matter, remember these are all the same. So I could take basically a vector and I can move it. And I'll tell you how to get the points later. But I can move it. So this is now hitting my origin. And so my initial point, I just moved to my origin. And here is my terminal point where my vector ends. And so maybe let's call this AB. So this is the point AB. So then we know, right? We know what our y value of that point is B, is the height. This is our length. Guess what we're going to do? Good old Pythagorean. So that magnitude, and we denote magnitude with a double bar around it. Vector. Sorry. So magnitude of vector V, which I'm just going to write as V with a vector, is written. So we don't have to write it all the time, with a double bar and then vector V. Kind of like absolute values, but two horizontal or two vertical instead of one vertical line. And so we can say that then this is the same thing as Pythagorean theorem, square root of a squared plus b squared. Guess how you find theta? Well, if we know a point, the terminal point, and our initial point is at the origin, and we have opposite and adjacent is tangent. So theta could be the same thing as tan inverse of y over x. Okay, but these are not always positioned where it's at the standard position. So we can figure out how to do that. But before I do that, one other thing I want to talk about is the negative. So if I look at the negative, so my scalar is -1, and I multiply it times a vector, this vector has the same length or same magnitude as V, but heads in the opposite direction. So kind of like when we were talking about polar coordinates, when we had r times theta, if r was negative, it had the opposite direction than what theta was. So it has the opposite direction. Okay, so now let's look at adding vectors. And we're doing this geometrically first. So when we're adding real numbers, they're commutative, meaning we can add them. If 1 plus 2 is the same thing as 2 plus 1. They are associative, so I can move around parentheses and still get back the same thing with multiplication and addition. Same idea with vectors. Not all things are commutative. For instance, if you were looking at composition of functions, unless they were inverses of one another, they're not commutative. I can't take the composition of f of g of x and get back g of f of x. Matrices, if you know matrices, you can't multiply order matters. Okay, vectors, adding, it doesn't matter the order. So that's just one rule that you know. So if I take some vector v plus w, this is the same thing as w plus v. So this is a commutative rule. What I was saying with the associative rule, so maybe you have a vector u plus parentheses v plus w. This is equivalent as if I would add u together and v, u and v together. Then after I take that sum, I add w. If I take a vector and I add it to the 0 vector, it's the same thing as if I took the 0 vector and added it to the vector, and I would just get back the vector I was adding to the 0 vector. If you add a vector to the opposite, the negative of that vector, this will give you back the 0 vector. Okay, there's two ways to add them geometrically. Basically, the first vector you're going to draw. The second vector you're going to take and you're going to put the initial point of that vector on the terminal point of the first vector. And then once you've drawn that, then you're going to connect the initial point of the first vector to the terminal point of the last vector. So for instance, let's say we have, this is our vector v, and this is our vector w. So if I wanted to figure out what v plus w is, shoot. So I'm going to take my vector v first. I'm going to take the same direction, same length, and I'm going to draw it. Now I'm going to take my vector w. I'm going to move it so that the initial point of w is hitting the tail or the terminal point of v, and then I'm going to draw the same direction. So the sum of the two vectors is going to be that line, again, that joins the initial point of v and the terminal point where w landed. And this would be that vector. So this vector here is v plus w. So notice that we'll find that also when we do w plus v. So our vector will look almost identical to this. So part B, let's find w plus v. So if we first take w, draw it, now we take v and we put the initial point at the terminal point of w, and then we draw it. So our vector v or w plus v is going to start at this terminal point, or I'm sorry, the initial point of w, and the terminal end at the terminal point of v. So notice that these are the same length and the same direction. So there's another way to draw these. The other way is to make a parallelogram. So basically, and this is a case where you might want to do this if you have two vectors. So let's say that they were starting at the same position. And so let's say that, for example, that we have, this is V, and we found that this was here, let's say W. To find the sum of V plus W, basically you're going to make a parallelogram. So what I'm going to do is I'm going to extend V from that spot, and then I'm going to extend W this direction. And it's going to be that line that joins the diagonal between this. So this would be W plus V. So when we sum two vectors, that vector of the sum of those two vectors is called the resultant. So the vector formed by summing two vectors, or summing multiple vectors, because it can be more than two, is called the resultant. Okay, so let's say you're given a picture, three vectors, and you're given that W looks similar to this. You're given that U looks kind of like this, and V looks like this. And it wants you to find U minus 2V. Okay, so let's look at what negative 2V is. So this is another way to write U plus negative 2 times vector V. So the negative is going to make it in the opposite direction. And the 2, it's going to double the length. And so now we're going to go here. Maybe you can do it above it. So opposite direction, but that length is twice that. So this is negative 2 times V. Okay, so now if we want to draw U, so U is this length, so we can put it down here. Oops, maybe let's put it over here because of my direction of the other. So let's put U here. Same direction, same length. So negative 2v.
Thank you, Heather Nicole. I love you, but it's nasty. I'll try another one. What's it? I think you gave me a strawberry. I'll try that one. So
Okay, sorry about that. So U, now 2v. So now I'm going to take this 2v and I'm going to put this at the tail. So, and I keep saying tail. We're going to put this at the initial terminal point. And so right here, 2v. And so the resultant is going to be the line or vector that joins the initial point of U to the terminal point of negative 2v. You should be able to do multiple ones. So for instance, let's just do one more and then we'll take a break. What if it told you to look at 2u minus v plus w? Okay, so 2u, let's make 2u. So it has to be the same direction, but it's going to be twice that length. So I'm just estimating. Minus v, so that would be our v value, but in the opposite direction and the same length. So minus v. So let's see. Sorry, it's hard to do this. It's about that. It's about the same length. So this is minus v. And then plus w. Where's w at? W is right here. So w plus w, so we're doing this at this point, and plus w, so it's the same length and same direction. Well, this looks like a bizarre one. Of course, I came up with it. Let's see. Let's do it more like this. Okay, and so this right here was W. So basically you're taking the initial point of the vector that you started. So this was our initial point at 2u. And then the terminal point at the end. And we're going to join them together, and that would be our resultant. So this vector right in here is a result of this in here. Okay, so after break, we'll look at, looking these and maybe moving them so that we have initial points, and then showing that these would be identical, or this was what would you would get if you did it algebraically and geometrically. But let's take a break. Okay, so we're continuing on vectors. And so now we're going to look at a vector, and it's called a position vector. I believe that's what it's called. Yeah. So the position vector, this is the vector where the initial point is at the origin. So if we have some vector, and let's say that this is a point at AB. The vector V can be written algebraically as, so it's kind of like a less than symbol, the component A, and then comma B, and then kind of like the greater than symbol, kind of sandwiching the A and B. Kind of like a point, except a little bit different on the ends instead of the parentheses. So basically A is the horizontal component. And B is the vertical component. You'll see here that we can see that our vector has the magnitude of V is equal to, again, Pythagorean theorem, the square root of A squared plus B squared. And this theta has to be between 0 and pi. Is tan inverse of y over x, or in this case, b over a. The unit vector is a vector that has magnitude of 1. And so let's say U, that vector U, is a unit vector. Then we can say the magnitude of U then is equal to 1. I, they usually call it I, is equal to the unit vector, where your horizontal component is 1 and your vertical component is 0. J, this is usually written as a unit vector. The vertical component, so the horizontal component is 0 and the vertical component is 1. If you have a vector Z, which is at AB, so standard position, Z could be rewritten in terms of I and J. So this would be like the scalar A times your vector I plus B times your vector J. So these are both represent the same thing. Finding a position vector though, so not all vectors are where the initial point are starting at the origin, and so rewriting it, because they're equivalent as long as they're the same direction and same length, finding the position vector is helpful. So finding the position vector, so let's say P sub 1 is equal to the point X sub 1, Y sub 1, and P sub 2 equals X sub 2, Y sub 2. And we want to look at the vector. Between P sub 1 and P sub 2. Let's say that this is equal to vector V. So to rewrite it, P sub 1, P sub 2, to be a standard vector, or sorry, a position vector. And then what you're doing is you're subtracting your X values. So X sub 2 minus X sub 1, that is going to give you your new X value, and subtracting finding the change in your Y value. So Y sub 2 minus Y sub 1. Maybe let's say not V equals this, but let's say V is the position vector of P sub 1, P sub 2. Okay, so let's pull some examples out. So the vector V has initial point P and a terminal point Q. Find the position vector that is express V in the form of AI plus BJ. So let's say you have initial point, which is at -3, 2, and Q is equal to 6, 5. So let's just look at that vector real quick. So let's plot those points. So at -3, 2, we have a point P. and Q is at 6, 5. And so we have this vector here. And we want to move it so it's the same vector, but it's the position vector, and it's starting here instead of at this -3, 2. Okay, so let V equal the position vector. So V is equal to the change in our X value. So our change in our X value is 6 minus a -3. And the change in our Y value is 5 minus 2. So this is going to be 9. 5 minus 2 is 3. So our position vector, so if we regraph this, is at 9, 3. So it should be the same length, same direction. Okay, so it wanted it in the form, right? V in AI plus BJ form. So our vector V, this is equal to 9 times I, that unit vector, that would have been here, but if I multiply that by 9, 0, 1 by 9, that gets me here, plus B, so my B value was 3 times my component vector here of 0, 1, J. So what if it says find the magnitude of vector V, and you're given that V is equal to 6I plus 2J. Well, if you graph that, you're going over 6 to the right. Oops. And up 2. You have our triangle. And so the magnitude of V is equal to the square root of 6 squared plus 2 squared. 36 plus 4 is the square root of 40. Square root of 4 is 2. And then we have a 10 underneath the radical. So if you're given your vector V, let's say is 3i minus 5j. And W is given to be -2i plus 3j. Answer the following questions. So what is 3 times vector V minus 2 times vector W? Well, when we're adding, and I didn't do this yet algebraically, but when we're adding two vectors, you're basically adding your horizontal components together and you're adding your vertical components together. And that's going to give you the components of the new vector. And so if we have 3v, so we're basically taking 3 times this vector here, 3 times I minus 5 times j minus 2 times, think of it as negative 2 times vector I plus 3 times j. We can think of it with a distributing property. So this is really like 9i minus 15j. This will be plus 4i minus 6j. Let's add our horizontal components. So 9 plus 4, so this is 13i. Negative 15j minus 6j, that's negative 21 vector j. So they say find the magnitude of v plus w. Well, we have to look at first the vector v plus w. So basically, we can look at this, v plus w. So let's just look at it here. So v plus w, we're going to get negative 3i minus 2i. So that's going to be 1i, vector I. Negative 5j plus 3j is a negative 2j.
Where'd you get negative 3i?
I didn't. Did I say? I meant positive 3i minus 2i. Is that what I said? So this right here, if we think of this as our vectors and we graph this in the position vector, then this would be at 1 and negative 2. So we would be down here. And we can think again about we're looking at magnitude. So we're looking at this length. And so to find that magnitude, this is equal to the square root of our 1 squared plus 2 squared. So square root of 1 plus 4, square root of 5. Just make sure I get everything. Okay, so sometimes we want to find a unit vector. So we want to find a vector that has length 1, but is going in the same direction as a vector. So there's a theorem. And the unit vector, we call it the unit vector of the vector that we're trying to find, the same direction. So the unit vector is a vector of magnitude 1
Am I reading that right? Does it say like the unit vector is AF?
Yeah, I couldn't erase it there. It wasn't erasing when I was trying, so I'm like, I'm just gonna skip it. I'll come back and try to erase it later. So no, so that F shouldn't be there. So theorem, the unit vector is a vector of magnitude 1 that has the same direction as V can be found the following way. So this unit vector would equal our vector V all over the magnitude of that vector V. So let's look at an example real quick. So finding the unit vector. Find the unit vector in the same direction as V. So let's find the unit vector in the same direction as V, which is equal to negative 5i plus 12j. Okay, so basically if we graph this, we want to rate this vector. So it's the same one, but instead of this length right here, we want it to have that length of just 1. And so we want to use this formula. And we first have to figure out what this magnitude of our vector is. And so our magnitude of that vector, so again, we can think of it as using the Pythagorean theorem, the magnitude of vector V, not length 1, it's a square root of negative 5 squared or 5 squared plus 12 squared. So square root of 25 plus 12 squared is 144. So 25 plus 144 is 169. So the square root of 169 is 13. So the magnitude of V is 13. So the unit vector, the length of magnitude 1 with the same direction as this vector V, we're going to look at vector V, which is this negative 5 vector I plus 12 times vector j all over the magnitude of V, which is 13. So let's just split this up and rewrite it as 2 separate fractions. So our unit vector of V is negative 5 over 13i plus 12 over 13j. So if I go over negative 5/13 and up 12/13, so it wouldn't be as far up as I had it there, that would be the length of 1. So theta, because sometimes you have to figure out what this is, right? This angle. Theta can be found by the following. Well, it depends on which value that you want to look at. Let's see. Where did it go? It's not really in here. Okay, so skip what I was just going to say, but basically vector V, this is equal to the magnitude of V all times cosine of alpha times our vector I plus sine alpha vector j. Here's a new rule. So if I had looked at this, right, and let's say instead of me calling this theta right here, I called this alpha, it would be telling me for this vector v, I'd have to find my magnitude, my r value. Remember this here? This was a unit circle. It would just be cosine of alpha. But because of this radius, this length here, this point was r cosine alpha I. Or I can think of the r here as the same thing as the magnitude of v. So to me, that makes sense that that would be another way to express our vector v. Do one more example. So write each vector v in the form a time vector I plus b time vector j, given the magnitude v and the angle alpha that it makes with the positive x-axis. So we're given that the magnitude of our vector v, this is equal to the length of 8, and our alpha is equal to 45 degrees. So if I was to graph this, I go up 45 degrees, I go out 8, so really you don't have to think about this formula. We should be able to do it without that. So think about, we don't know a couple of our sides. Think about the trig functions. And so if I want to figure out what x is here, or in our case, they call it a. So if we want to figure out what this length a is, we know our alpha, which is 45, and we have our hypotenuse. And we want the adjacent. And so that would clue you in to use your trig function. And so I know that cosine of 45 degrees is the same thing as a, my adjacent side, all over my hypotenuse 8. So a is equal to 8 times cosine of 45 degrees, which you should know. A is 8 times root 2 over 2. So this is equal to 4 root 2. My b value, or my b value, so this is opposite, and I have hypotenuse, so that should clue you in to use sine. So sine of 45 degrees, this is the opposite, which is b over our hypotenuse of 8. So we get b is equal to 8 times sine of 45 degrees, again is root 2 over 2, which is 4 root 2. So we know what a is and we know what b is, and so our vector v is equal to 4 root 2 times vector I plus 4 root 2 times vector j. Okay, so we got through most of the main, all of the main, the math stuff, and then we haven't really looked at any application. So we might look at 1 or 2 applications tomorrow as we review for the final. But that's pretty much it for 10.4. And so that is all pretty much the new material you guys are going to get for this course. Let me stop the recording.